Good. Okay. The moment we mention Planck, we need to go quantum. And you may say, what could be quantum about diffusion in external potential? So again, everything is dimensionless, so one-dimensional. So we consider a very simple problem, minus dv dx, and eta is a random white noise, namely that eta of 0, eta of t is equal to, how I divide it, to temperature delta function of t. And so what we know that d rho of x and t over dt is equal t dx plus d dx rho dv dx acting on rho. Wait, like this. Okay, so now I would write it, what is essentially quantum? Quantum is a kind of pretty simple. It's a linear algebra, essentially. So I would write it as some operator. I'll call it Fokker-Planck operator acting on rho. Well, this is a second order differential operator. This is some known function. This is just the first derivative. And because of kind of perverse nature of education, people usually learn quantum mechanics before they learn fluid mechanics or, I don't know, diffusion or something like this. So maybe this language will be natural. I spent maybe 5–10 minutes on it, but we need to cool down to quantum anyway. So in a sense, when I use a quantum language, it's essentially algebraic language. I say that my rho of x, you can think that I have a state psi, and this is just its projection on x, right? So I will kind of use this notation. So in a sense, I may say that this is the same as I do d dt of a state psi. Rho are functions. This describes evolution in the space of function. I can say, okay, this is my Hilbert space of function. So I can think of states in this Hilbert space, and this satisfies this equation times psi. But on the other hand, I can, and I know a formal solution of this. So like psi of t, if I want to get it out of psi of 0, then I need to take exponent h, this operator, and act during the time t. The only difference is that there is no I here. Incidentally, I remind you that Schrödinger equation is almost like diffusion equation, right? So if I take a stationary Schrödinger equation, right, acting on psi, it has the same Laplacian which look like diffusion, but it's I here. It's what this quantum people always say, that you live in an imaginary time, and we statisticians always say, no, you live in imaginary time. So this is the difference, that in quantum mechanics is usually imaginary time, and here it's a real time, but otherwise it could be written like this. Why I'm doing all this? Because I really want to write it on a conditional probability, which is, you know, in quantum mechanics as a transition probability or green function. So I would like to write it on a quantity which will be working with regularly. What would be a probability to be at xt under the conditions that you were at x prime at point 0, right? And then I say that, okay, now according to it, this must be a matrix element between how I put my times. No, I actually put it like this: x prime t prime xt. So I wanted to have the whole So it's between x prime and x. And what I have here is an evolution. And again, this state x means this psi, h t prime minus t, right? So this is a formal way to describe the conditional probability. And why I'm doing it? Because I now want to discuss the symmetry properties which I have for a different state of my system. Okay, and in particularly, if I don't have any external potential, I know that my space is just diffusion. All points in space are totally equal to each other, and I have a simple symmetry property of x prime where is this? Yeah, x prime t starting from x at 0 must be the same as the probability to starting from x prime at 0 at time to x at time t. This is called detailed balance, right? So this is something which is a totally kind of my starting point. What now I want to discuss, what if I am in the external potential, which depends on coordinates somehow, and I would like to know if there is any kind of a balance in a steady state. For this, I need to ask, what is a steady solution for this equation? And the steady solution for this equation, again, another form to write it, as you probably remember, is ddxj of x. Well, j, which is, if you take ddx over here, this would be j. So it's pretty easy to write stationary solution of this equation. You have seen it many times in the course. Let's call it rho naught of x. It's what? Let's guess its form using information theory approach. So the only thing I know about my particle that when it is in the position x, it has an energy v of x. What might be the probability distribution to be an x? It must be exponential of what I know. It's always like this, right? It's called Boltzmann distribution. I'm sure you have seen it many times. It's 1 over z naught e v of x divided by t. This is a Boltzmann distribution. It's straightforward to plug it here, and you see that it's ddx plus dv dx. So when you differentiate this distribution, you will see that you differentiate this, and it turns into 0, the Fokker-Planck equation. And of course, it satisfies the general condition that whatever you assume is in the exponent. And of course, z naught is a partition function, which is it's a function of temperature. It's an integral e minus v of x over t dx over all x. Right? Now, for this state, how I need to modify this? Now, my place in space aren't equal, right? Somewhere potential is higher and probability is lower. Somewhere potential is lower, in the bottom of potential, the probability is higher. So now the probability to go from here to here aren't equal, because the probability to be there and there aren't equal too. But of course, it's equilibrium. And equilibrium means that there is a detailed balance. There is no current of probability, right? It's equilibrium, which means that this, you can check that this current J is exactly 0, right? But if I take this, thing, so how I need to modify them? The right modification, I first write it, and then I'll show you using this quantum language, which I essentially introduced for this. What you need to say that what must be now equal, not the probabilities of transition from here to here or from here to there. But I need to take each point of start with its own probability according to this distribution. So if I multiply here exponent minus v of x prime over t, and if I multiply here by exponent of v of x over t with a minus, right? That would be a statement that now will be a total current. The probability to be here at x prime times probability to go must be the same as the probability of being here and go backward. That would be a detailed balance. Okay? Now, why would I use this operator language? That what we formulated on this language of transition probability must be some property of this operator, right? So it must be somehow encoded in this operator, because when I invert my evolution, when I exchange this, my h, fp, would go into conjugated h. But my h is not Hermitian, right? So if I look at h operator again, is t2 dx squared plus d dx dv dx. And its conjugated, of course, is t. This is self-conjugated operator. Diffusion does not care about it. But this would be minus dv dx d dx. It's a different operator, right? At the moment that v dv dx is a function of coordinate, namely my v is not a linear potential, it's not. So what I would now do, I would now translate this property, and I'll go up because I really want to be here close, so I will just write it over here. So what I would write this to translate it from the transition probability to operator, I would write it as a matrix element between x prime exponent minus t h minus v over t and x, because this is this, and what I added this, I added it here. And it must be equal to x exponent minus th minus v over t x prime. And now I exchange it by exchanging exponent, and what would stand here, minus v over t minus h cross times t, and here is x. So what I did essentially, I wrote this, but I wanted to have x prime here and x prime here. That what, because now it's true for any x prime and x, it's actually equality on these operators which are standing here. And so as a result, I obtain the following statement that this operator, which is h cross, is exponent v over t h exponent minus v over t. So it is a property of this operator, or in other terms, if I would multiply by exponent minus v over 2t and exponent plus v over 2t, it will be, now this operator is complex conjugated. Okay? So this is a property of Fokker-Planck operator, and it now works for arbitrary v. Okay? So that's what I wanted to show you, how in equilibrium, even in a very, very non-uniform equilibrium for which I impose external fields, I get a fundamental symmetry relation. And now, much, much more exciting thing. This was a kind of classics. And now, 21st century, what happens, and if we can have any relation, exact relation, when potentials start depending on time. So this is now a truly new thing, which means that a moment the potential depends on time, we're out of equilibrium, right? It's straightforward. If you take this solution and V is a function of t, and you plug it into this equation, it's not a solution, right? The right-hand side turns into 0, but the left-hand side has this extra term 1 over t dv dt rho, right? You just, and it's not, which means that you can, for example, assume that you start initially from this distribution at some time equal to 0, you take this, and this is true. So you start from a statistical distribution. It could be delta function at initial moment, depending on what form of your potential you take. And then you start evolving it, and you ask, can you derive any exact relation? And to my surprise, it's turned to be possible. And then there will kind of, was like maybe 30 years ago, the first relation. Now there's kind of a booming business of deriving such relation. But what is amazing is that it was first derived pretty technically, in the sense that this was asked how we can get rid of this term, right? So we need to consider something else, the distribution. So we need to take this rho, which we are interested in, and kind of weight it, to add some extra random variable, so that for this new thing, let's call it W, when we write the respective equation, it would be now in an extended space. So it will be current in the direction of x, but it will be also current in the direction of some other quantity. And we need to write in this multidimensional space and see if it can have some kind of a universal form. And and it was derived in a very roundabout, very technical way. I myself learned the way which I now will be telling you much, much later, and by one of my postdocs. He actually invented this way of a simple derivation that I will now show you. But after we'll derive it, you'll see that it's very, very natural. And it's just amazing that Boltzmann did not derive it, or Gibbs, a genius. So what this quantity W that we consider, and again, for somebody who already learned information theory, would be very, very natural to consider. It's a work. That's why we call it W. And it's a work done by this external potential. So again, what we are doing, we have a particle with external potential. The particle has its random thermal motion, but it also moves in this potential. The potential changes with time. It means that it's always the potential somehow applies force to my particle, but this force very much depends on where a particle is, because particle move randomly, right? And okay, so but somehow, okay, yeah, okay. So let me. So it will be a function of time. It will be integral from 0 to t. And you remember that at 0, we start from a Gibbs distribution. So we have particle, ensemble of particles which are placed with the probability according to their, and then we start changing. So we'll integrate over time dv over dt prime, but v depends on x, which itself depends on t prime, and of t prime. Right? So now it is something which is taken at the position of particle, and the position satisfies this equation, right? Which means that this quantity has a double randomness. First, it's a randomness of x where it started from according to this distribution, and also it's a randomness of this noise which moves it God knows where. So this is, by the way, how you really do experiments. You You take your particle, you start from any position, and your noise is your noise. It's your thermal noise. So it's not a full derivative. It's only with respect to this I differentiate, right? Because if it's full derivative, that would be v at the end minus v at the beginning. No, it's non-equilibrium system. It depends on the whole trajectory. So now I want to consider this quantity, which depends on it, but I will do it very, very smart, which is, so first of all, what it would satisfy? It would satisfy the usual equation d rho dt t d rho dx squared plus d dx dv dx. But what must be here also minus d dv rho times v dot, okay? The speed in the direction, so how fast changes w, my work, right? And of course, w depends on time, it depends over here, so what stands here is dv dt. That's essentially why technically Yerzhinsky wanted this quantity. He wanted something of which derivative is dv dt, but really partial derivative under x fixed, right? That's precisely what we get when we did not satisfy this equation, okay? But it's not that simple yet. So now, and this is our equation. And what is the initial condition? The initial condition for the quantity x w0 would be rho naught of x. That's our rho naught, right? And in terms of w, it's just a delta function because the w was 0 at initial moment of time. So that's equation, that's a boundary condition, okay? And the question, if we can solve this equation, the answer is no, but we can solve it for something else. Namely, we introduce a quantity which I will call f, and it's an integral over f would be a function of x, right? Yes. And t, let me write it in the whole, x and t, it's an integral of w rho of x w t exponent minus w over t. So this is something which now approaches of making sense, even though it may look technically a little bit more involved, but it actually makes sense. So what we're suggested to do, we're suggested to take any such trajectory with this weight. This weight is exponent minus external work, external. Somebody changes this potential in which we live. Right? It's a particle, it's a system, right? The contact with a thermostat, it starts in a state with a maximal entropy because this is a thermal equilibrium. It definitely has maximal entropy under the condition of having this energy. Now somebody from outside start changing this energy. It could be positive, could be negative, you know. Somehow the potential could be like you're moving down the potential. You stop like this and you start losing your energy because you are now kind of going front. But it suggests that if you would really weight it like this, then something happens. So let's see what the equation we will get if we take this equation, multiply it by exponent minus beta w. Beta is 1 over temperature, right? Always, and integrate over dw. Right? So everything here would be just like it's kind of irrelevant with respect to w, will be just kind of the same function. But here I have this and I have that. So I need to integrate by part, and it would give me this extra term. And now let's see what I will get. I will get df dt plus, well, equal to t d2f over dx squared plus d dx f dv dx. And out of here, when I differentiate it over there, I get minus beta f dv dt. Okay? So that's what equation that I've got out of. So what I did it for, to get rid of this extra derivative over here. You see, on rho of w, I have this. And now on f, I have this just standing here. And this now has this form of a solution. Because now it would totally cancel. So if now I have this, remember, f as a function of x and t, it's exponent minus beta v the function of x and t. Okay? And what was it? Let's see. We know that this satisfies this for sure. But also, when I have df dt, I would have dv of a dt with a beta with a psi minus, and it kills this term. Okay? So, again, let me reiterate what did we do. We introduced some pretty strange and idiotic function. It's not a probability distribution. Its integral is not unity, right? What we did, we introduced a probability distribution in a wider space, and then projected it on x, taking every one with its work done up to this point. And this has an exact Gibbs form. Okay? But the beauty of it is in the integral relation which we get out of it. Is that now if we integrate f of x dx just all over, right? So what we obtain is that this is an integral over dx dw rho x w t exponent minus beta w, right? And I may say that this is exponent and now, because I have this quantity and it's every moment of time, it satisfies this relation. So what it essentially tells me, it tells me that it's equal to z of t over z naught, or if I write it in a specific way, that would be exponent minus beta v, well, sorry, this is v of x t dx divided by exponent of minus beta v of x naught dx. Okay? So again, when I take this, it has z naught because of this condition, and v of xt. When I integrate it over time, I get z naught in the denominator. In the numerator, I guess integral of this. Okay? So what it tells me, the following beautiful relation, that an average value of such a thing, which will immediately recognize the physical meaning of exponent of minus work done divided by temperature, it's totally independent on how we do the process. Those are end and beginning. nowhere during the process we are in a Gibbs state and have such probability, only in the initial moment. Okay? What still we get, that this quantity is so universal that it does not depend on how we do this process. On the other hand, experimentalists got totally ecstatic at this point, because this is, by the way, it's a ratio of, if you wish, it's an because the z is minus t, f is minus t logarithm z, it's exponent of f of t exponent of f of 0. So it's exponent ft minus f0. It's a free energy of an equilibrium state. If I end at this state v at xt and let system relax, it would get into equilibrium. It's that potential if I stop evolution at this point. And it will be its free energy. Okay? System is not in equilibrium at the end point, but it does not matter. This relaxation already would include no external work. So it tells me that I can measure difference in totally equilibrium quantities, free energies, using however fast process I want. Because I can compute this. It just tells you average over all positions of x. That's it. I can do it very fast, changing it very fast. It tells us something which for some time people did not want to believe, because we used to think that if we want to measure something about equilibrium, we need to do quasi-static processes. You see, yes, but there are some quantities for which you don't need to do it. For such quantity for which you can measure using whatever fast process you use. Well, if you don't incur some kind of extra losses out of it. Okay? So what it is this quantity that stands here? Why it so has such a magic properties? How would you interpret it? We have a system and we have something external, and this external does work on it. When you do work, you change a phase volume. You can compress it or you can expand it. So you do this work and you divide it by temperature. So what it is this here? If you compress a system, what you do to its entropy? You decrease it. If you expand the system, you increase its entropy. What is here is the change of entropy of your system if you also account for the change of free energy. So if I write it like this, exponent minus beta work done plus f naught minus f of t, also divided by temperature, incidentally. So what I get here is exponent minus change of entropy of my system. And that's a new second law of thermodynamics, much more powerful than the old one. What was the old one, by the way? The old one was, no matter what you do, delta S larger or equals than 0. Does that follow from this? Or that follow from this? Or they are unrelated? What property of exponent we use of any other function, and of logarithm too, we use over and over again to prove things? Huh? Convexity. So what convexity tells you about the relation between a mean value of an exponent of something and the mean value of this something? It tells you that if you have E of r average, it's larger or equal than E average of A, right? It's just this property that it's a convex function, right? So if you just, on any interval, and now right? But this is equal to unity, right? So what it tells me that exponent of minus mean change of entropy less or equal than unity, which exactly means that delta S is larger than unity. But this is much more, and it's an exact equality. Okay? So this simple, beautiful, and powerful. Of course, if you have any change of information over there, if you learn by your system something in the process, it would be, and it's another 20 Nature and 100 PRLs written about this thing. But what I really want you to show is how we replace 19th century inequality by 21st century equality. So this is a second law of thermodynamics. That's the form it has. It tells you that because the exponent of it, it's a phase volume, right? So it's essentially change. So if you account for all changes, but you need to take your works, changes of free energies, information, all in the exponents, okay? Then it would be phase volume, a pure thing which is just a linear probability. So this is, and of course, you can expand it. So this is just a first expansion of it at delta S small, right? But you can get many more statements, and so it's much more powerful. The question is it the most general form of a second law of thermodynamics that we know? And the answer is no. And this is again a consequence of even more general relation, which goes back. That's why I was bothering you with this Fokker-Planck operator, because it's more natural after. So you can again look at the language of a transition probabilities. And this I would give you without derivation. Maybe we can do it for how much I will have for Google. Okay, first of all, let me give you. So assume that I have a probability of going into the, how I would, yeah. So I have a probability of some process which led to the change of entropy delta S, okay? And now the statement is that if you multiply it by the exponent of minus delta S, this is just, now I'm not talking of averages, I'm talking of probabilities. So given delta S has some probability. I have kind of random, you see, this is a random quantity, right? In different trajectories of a particle, at some it gained entropy, and some it lost entropy, and some, this is, then I average. But now I'm talking about probabilities. It would be exactly equal to the probability of going backward in time, losing that amount of entropy. Okay? I may, if I have time after Google, I may prove it for you for Baker map, which we did before, or you may look into lecture. But this is something much more powerful because it's a statement not about averages, but about probabilities. Is that follows from it, let's say, without information? Of course, you just average it. That would be exponent minus delta S And this would be unity, right? If you just average, whatever is probability, it's normalized. So again, this is a consequence of this generalized detail balance. You know, as I've shown you, the generalized detail balance for a potential which is independent on time was easy. You just multiply it by exponent of initial Gibbs and of exponent of a final Gibbs. This is more non-trivial. It tells you that you need to weight it by exponent. It also tells you the following things, which again now is a booming branch of science, is that if you take rho of minus delta S, divided it by rho plus delta S, it's an exponent minus delta S. Namely, that for big system, this is a negligible probability. This is usually macroscopic quantity, right? But generally, when you're working with finite systems, and what we are doing now more and more, we're working with finite systems, then you may ask, okay, on average, I gain entropy, right? Whatever I do, my entropy increases. I forget information. But there are some realization of this particle where it so happily can, kind of be so happy with this potential that it can actually decrease its entropy, right? Yes, it's possible, but the probability of this divided by this is exponentially small in terms of it. And this is, again, a kind of a universal relation. And we very much hope that there is a kind of a generality here. But I just really want you to reflect on what banal and trivial system we're actually working on, right? We did it, derive it, for something which is a very, very specific. Now we try to, and we're sure that this some kind of analog must be for any system, but it's not easy technically to prove it. Okay? Questions? Maybe one analogy that I'll remind you. You remember when we were talking about mutual information, and we said that the Boltzmann statement that entropy of any one particle momentum distribution increases, and the Liouville statement that the total entropy of a dynamically interacting gas stays the same, it's the same statement. It just means that mutual information, you remember that we say that there was the sum of Si minus S of P1 Pn. And this is by definition equal to the mutual information between particles in a colliding gas. Boltzmann was claiming that this is growing. Liouville claims that this is conserved. We interpreted it as a statement that as we start from non-correlated particles, the mutual information grows. Here it was almost trivial to replace inequality growth of it by exact conservation of it. In a sense, this is in a similar spirit. We replaced inequality for a very specific class. We still work, the work is the beginning, by inexact equality. So if you weight every trajectory, then something is exactly unity. And your inequalities follow from convexities. That's where it comes, because there is an exact relation. Okay? Ready to talk Google, or you want to relax, meditate a little bit about it? Because unfortunately, it's not the break that I don't want 2 breaks, right? But I really want to consider second subject. So let's take a deep breath and spend 30 seconds relaxing. Okay. So now, while you are relaxing, I erase all the random walks in a real space, and we go into random walks in the internet. I hope this language of operator and states, it's not, I mean, you all learn quantum mechanics in some form, right? So it's not that, well, it will be so much quantum mechanics starting from the next lecture. And by the way, while we're relaxing, there will be now one lecture per 2 weeks, right? Because there will be no lecture on November 11, there will be lecture on November 18, then there will be Thanksgiving, and there will be no lecture on November 25, and there will be last lecture of December 2. Okay? So the next lectures are November 18 and December 2. And that would be quantum information. Okay. So now what I want to tell you that if you really can exploit someone very well, you can earn a lot of money. And if it's not a person, it's even better. So the people who learned how to exploit random walker, those people who gave us Google. But again, you probably know this. One of them was really doing PhD. So this was a PhD work, and actually a paper published in a journal. And I very much advise you to read it. It's very readable. You can find it, I guess, in my lecture notes somewhere. I probably gave the reference. So the problem is, which we more or less try to avoid up to now, is importance of information. Right? So in a sense, the great advantage of Shannon was just stripping meaning out of messages, just treating it as a random sequences. That was considered truly idiotic at the beginning. And that was, of course, very powerful, because if you are really working on transmitting messages, you don't care what is written, you really care about statistical law of big numbers, how to do it most effectively. And then people were so much impressed by this, they started to say that there should be no meaning, that the moment that meaning appears is just philosophy, it's not information theory. I still remember this totally meaningless discussions, and we actually already tried to introduce meaning. You remember when we were doing this information bottleneck from B to A and then to coding into C, we already introduced I between C and B as kind of a meaning, right? What is here that really we need to encode? And the author of this paper, I know them personally, they also try to argue that this is legitimate. You can try to introduce meaning into information theory. But at early days of internet, the problem was much more acute. And I'm old enough, I remember these days. Searches were unbelievable. They gave you, just read the paper of Brin and Page. It gives an example what you get out of typing Clinton, for example. That Clinton was the president at the time. You get some Clinton bridge at some county. I don't know. So the way that internet searches work was totally idiotic, and essentially it was this feeling that we have a Bible library at last. So we do have now a library with a huge number of books, of pages over there. We just don't know how to find what is relevant, because to find what is relevant, somehow we need, there are too many things where any given object is mentioned. We need to rank them. Okay? So there was a problem which was essentially trying to rank importance of a given web page. And the moment you ask like this, it seems more or less, again, evident that now you again back to not arguing who likes whom, but you argue who links to whom. Right? So essentially, you may say that, let us think that there are important pages for which you can come from many, many other pages, right? So the page is more important if there are more pages that actually use it, namely link to it, okay? But then you also ask, okay, but how much importance that other page bring to you? I'm probably telling you things that you know, but I still kind of want to, that, yeah, if I have a page which links to me, it also has its own importance, right? for the same reason. But it shares this importance for me inversely proportionally to the number of links it sends. Because if it connects to many links, then I get a little bit only out of its small fraction. And if it only refers to me, which means that I'm really important, etc. So this was a kind of a basic idea. And of course, probability immediately started to creep into it, because at this point, you kind of assume that it will be something which would be determined how often you actually can get from here to there. But technically, so what you say, okay, let's introduce a vector of unbelievable lengths. A vector P will be P1, Pn, and this is the total number of web pages in the internet. Believe it or not, but Google crawlers really work with this vector. Okay, so and you want it to be just for the simplicity of it a probability distribution. So you want sum of pi's to be equal to unity. Okay. You say that this is a vector of ranks, which be also a vector of probability. The more probable is to get to this page, the higher is the rank of this page. But you need to say which is actually the law. And then first you say, let's divide it as a rank, as we say. So we say that pi, it's now not it's a component of vector, but this is a given web page, is a sum over all j of pj's, namely, this is the rank of a paper of a page j, which links to I, but you need to divide it by a total number of links going out of page j. That's it. That's put into formulas the statement about rank that I did. Every page has a rank, which is rank, sum of ranks of all pages, who links to it, divided by the sum. Actually, instead of this, you can be a little bit more sophisticated. You can try to, and that's what now Google really does, to use real frequencies with which it links to different pages, so that the sum of it would sum into unity. But for now, it's like this. So this is now means that we are looking for an eigenvector of a matrix. So we have a matrix, right? And this is a matrix is such that it has entries which are 1 over nj's for different j's, right? And it's kind of a sparse matrix in which you only put these numbers where you have links. And of course, the sum, now, if you sum over p i's, you would get unity, right? So this is such a problem. So you are looking for so this is aij is 1 over nj if I and nj are connected on the way j to I, right? So you look for this eigenvector of a big matrix. First of all, you need to get this matrix, right? That's what crawlers do, right? They always go through the internet and they just record most of the activity of all servers on this planet is this work, well, probably, not maybe most, but substantial part of it. Somebody gave me numbers, just hours, mostly in Kazakhstan, for some, because the energy is cheap in Kazakhstan. There are these servers. Yet, how to find it? It's an unbelievably large matrix, and you're looking for eigenvector. Moreover, you want eigenvector with eigenvector unity, right? So if you want this solution of this equation, that you really need to find. So apparently, you need some iterative algorithm, right? So again, how you do iterative argument, you need to start from something. What you start is pretty natural. You assume that all pi's are just t equal to 0, you assume that pi's are just 1 over n. So you assume that they all the same, all pages have the same rank, and now you need to do iterations. How you do iterations? How would you do iterations? You are PhD students, right? So that's precisely what PhD students, there were a couple of other people who were doing similar things at the same time. They said, let's consider the same matrix A, because if we really want it to be a converging iterative process, that let's do it like this. Let's take P of t plus 1 if time of t, A. And A is, by the way, time independent. So this time is your iterative time, right? So what you really take, you take this, when you multiply by this matrix, apparently this piece which will change, because some of them get multiplied by this number, some of them do not get multiplied by these numbers, right, etc. But the question is whether this process is really converging, whether this iteration converge, and how would be the evolution. And then you immediately recognize that you have two big problems immediately. One is a problem of loops. For example, you can have state 1 and state 2, and what you have is this, right? So the idea was like this. You start your random walker. That's where the idea to exploit somebody came in. With random probability, you start at any page, and you let it go. You let it go with the probability changing like this, right? Now, if you start at page 1 and it's only related to page 2, you'll be going back and forth like this. There will be no according to this matrix, right? So if you happen at this point, there's the only operator which acts on you with the probability 1, you would go this and this. And there is another problem of egoists. So there is some website of which you get people, other sites, link to them, and they do not link to anyone. It happens. Then, if you start, for example, at 1 or at 2, no matter how small are these probabilities, you eventually would end up in 3, right? So any random walker at whatever web page it starts, if it gets into 1 and 2, it would end in 3 and would stay there forever. So your process would be stuck. It will be either stuck in a loop or it will be stuck in a sink. So how to overcome it? Again, it's all about a skillful use of a random walker. Yes?
Well, you could make it bidirectional. You could convert, you could take the matrix's average of its reflections, so you just are assuming that each link has equal weight in both directions. And
as each link is what?
Has equal weights in both directions, so that you can go through them the other way as well.
No, look, if I link to President Biden, I cannot request that President Biden links to me with the same probability. This is just, reflecting links, this would be, people link for reasons, right? For reasons of information. So apparently links are information, but you want to introduce a little bit of randomness, which would kick you out of being trapped here. So to get out of a trap, you need to just allow to go somewhere. And that was the idea. It's very, by the way, I maybe cited how they, because I just took a quote. We assume there is a random surfer who is given a web page at random. It keeps clicking on links, never hitting back, but eventually gets bored and starts at another random page. So the idea was that on any page, and this must be uniform, because, just not to specifically, you cannot look for them. You just, with any page, you take the probability of just not using bookmarks or links or whatever, just go somewhere. That was the idea. Nobody at this point knew that it would be practical, but you can prove mathematical theorem, and in a moment we will prove it, that it would work. Okay? So this was a mathematical work. This is what the people did. So what they essentially did, they replaced A by a new matrix G. Not surprisingly, it's called G. And it is dA plus 1 minus d. This matrix is called teleportation matrix, which is essentially E is a vector which is 1 over n to 1 over n, right? So this kind of an analog of a unit vector, and yeah. So so this is a random. This is a matrix which has a uniform. All its entries are the same. Again, it was original version a little bit. Yes. So what you actually, by using this matrix, now at any site there is this probability to jump to any other site. It's unbelievably small. It's 1 over n, but still it exists. I mean, it's unbelievably small for any given site. Now, what is D? D is something which, again, must be determined by how you want your process work. So essentially, the achievement of Google's was the following, that they considered iterative process again. What you want of this process? You eventually want it to stop. If you want it to stop, it means that at some time this and this will be the same, which would mean that you kick on eigenvector of a matrix G. Moreover, it's an eigenvector with a unit eigenvalue. Okay? It's quite clear that such matrices cannot have eigenvalues which are larger than unity or smaller than unity, because if it's larger than unity, it would blow up, and sum of p's is unity. And if it's lower than unity, it would go to 0, and again, sum of p's is unity. But you aren't guaranteed that this is really converging to it. Moreover, if it really has such an eigenvalue, which is unity, then you have a second eigenvalue, lambda 2, like this lambda Lyapunov expert. And this must be less than unity, right? All other eigenvalues must be less than unity, and it gives you the rate of convergence. Okay? Now, it's a non-difficult but non-trivial exercise to say that if I have whatever matrix A, and the matrix here, which is all the same elements, then eigenvalues are 1, d lambda 2 of A plus etc. plus d lambda 3 of A. So in a sense, you have eigenvalues of A and eigenvalues of G will be again sharing the same unity, which we'll show in a moment. So initially, and this gives you the rate with which you converge, because it's less than unity. So eventually, you would have a convergence by this rate, right? This is something which is less than unity. So whatever deviation from your eigenvalue would be decaying initially with all eigenvalues, but eventually would decay with the second one. This will be long surviving. So of course they wanted D to be smaller, because you want it to be smaller. But when D is smaller, you stop respecting the true structure of an internet, because it means that you just replace everything by, with almost probability 1, you will be jumping somewhere, which means that now that will be very low probability. And this is precisely like, you remember, always in our optimization problem, we always have this beta. we say that E, we always have this beta which tells you how important for you, first of all, to go fast. Because if you make diffusion, more diffusion, you faster would go where you go, right? And respecting the true information which is there. And if I'm not mistaken, it was 0.85, right? Let me check it. I don't remember where I put it. Yeah. Well, it's. I think it's. So this is empirically, they took it 0.85, and again, being very empirical here. Namely, they just look how much, how often people use bookmarks and links on the page, and how often they just go somewhere. Okay, and after that, amazingly, it's about 50 iterations on average, right? But let's now prove what they were using was called Perron-Frobenius theorem. So what we really now, what is the difference? The main difference between G and A. A had 0 elements, and it had loops. G does not have loops, and it does not have 0 elements. Namely, G, if you somewhere, you will go somewhere. You won't be stuck there. Such matrices are called, we already, by the way, mentioned them. It's called stochastic matrices. So Aij are they are positive, and sum over Aij equal to unity. Okay, this matrix is called stochastic, and for such matrices there exists a beautiful theorem which tells that they do have a eigenvalue which is exactly equal to unity. Well, this Perron-Frobenius originally just have it for just saying that it's positive, but we already normalized. So our P is normalized, so our matrices are normalized, okay? So this is now J, by the way, no A, because we are now talking about properties of a matrix J. So Gij positive, Aij are not, and Gij, the sum is equal to unity, okay? And so now, because of this property, it means that if I take E transpose, namely the vector of all equal things, and multiply it by G, it will be the same because the sum is equal to unity. So I do know that the transpose, that the G complex conjugated has an eigenvalue unity, but G must have the same eigenvalues which G complex conjugated. It's not an Hermitian matrix, but they have the same eigenvalues. And this property guarantees me that this is a unit eigenvalues, which is essentially what we mentioned when we measured that this is. So now you can also argue that if you have P and you multiply it by G, I mean this thing, right? So this is a vector and the matrix. This is some convex combination, right? So this is P J, G, I, J, sum over J, right? So it's a combination of Gij, of which sum is unity, which means that it cannot be larger than any element, that's the largest element of P. And if I had eigenvalue which would be larger than unity, I definitely need at least some largest part to increase. So essentially this statement, it's kind of convexity, because if it's eigenvector, that this is the sum of this combination, and this is never actually larger than largest element. Okay, and Yeah, 845. Yes, that's right. I find that this is 45. Now, how one might, this is a very basic a skeleton idea. So the understanding was that you need a rank. You need to exploit random walk. And this is indeed random walk. So and for this random walk, you need to avoid it being stuck. And then you have these beautiful theorems which tells you that you do have such eigenvalue. The moment you guaranteed that it's positive, and you still, because you keep probabilities, and you still have your normalization. How you can improve it? One thing is that here you can get individual, in a sense that, and that's what now is done, that you can replace the equal probability to jump anywhere with some kind of personalized probability. Where do people really jump? Because people very often jump to news, etc. And each one, by the way, and this I think probably will be some next great startup, or maybe Google will give this service. Not for now. You can have your personal search engine, because again, into this matrix and into this matrix, you can introduce your own personal information about what you actually want. Incidentally, because I'm an old person, I remember how Google was much better than, for me personally, was much better. First of all, there would be less advertisements. They do need the billions of dollars, but it's very often irrelevant, right? And it's irrelevant in a sense. Of course, then you learn how to use. So it's an art to do Google searches, and Google Scholar it's even more art. But it's something which could be really put into infrastructure, and this I probably would be done tomorrow. I won't be surprised if you can really order your own search engine, which would be giving you what you would more likely rank higher than average surfer, faceless random walker, which walks somewhere over there. And of course, there are things which you can put here, but again, it's something which is not easy to do because it should foresee your future searches, right? Which means that it's more or less, it's like the truth, the whole truth, and nothing but the truth. You need to leave everything outside as it is, and only something for which it is enough statistics of your personal things, it can change. Okay? Good. So I want to finish at this point. So really what I want you to, example of Google, I think it's nice because first of all, it's really important things that I want you to remember about stochastic matrix. We already mentioned it. I mean, this is a transition probability, right? This transition probability which we first encountered when we discussed correlation between letters in a language. What is the probability of having this letter after this letter? And of course, another thing that I really want you to remember from today is this and this. This is pretty simple, as long as we get it. It's still very difficult technically to do it for, I mean, rigorously, etc. But it makes much sense. And it shows that in such a classical subjects like a second law of thermodynamics, it's still possible to do new great discoveries. Okay? Good. Any question? Good. So guys, we part ways for 2 weeks. Yeah, question?
So, in that equation, it's tempting to see as like the entropy, the first and second term being some form of entropy, but the E matrix.
Yeah, in a sense, it's not a free energy for which you look for a minimum. It's your matrix of transition probabilities. Okay? So it is in this matrix that you introduce, you may say that this kind of an entropic element, because it's a random element which immediately opens you like to anywhere, which makes holes in your walls of your prison, right? But literally it's not entropy in the sense that it's not a logarithm of any probability average. It's just kind of an entropic way out. Okay? Okay, so see you on November 18. Don't come on November 11. I'll be in Europe, and will be quantum for the rest of their life. Okay.